So welcome to the next installment of the C-Cube seminar. Our speaker today is Professor Peter Veerman from Portland State University. He's a professor of mathematics there. So Peter got his PhD in applied math from Cornell in 1986. And after that, he spent his time traveling all around the world: Brazil, Spain, Georgia Tech, Penn State, and God knows where else. And finally he settled down at Portland State. I don't know why, but that's what he chose. From 2000.
You make it sound really bad.
Well, I visited that place. It's actually nice. So since 2000, he has been at Portland State. And the way I actually came into contact with Peter was that I was working on these platoon problems, and I learned from a very complicated set of routes that Peter was also working on it. And then he invited me to come over there, and we talked. And since then, we have been kind of collaborating a little bit on those problems. And Peter has been doing a lot of interesting stuff on these very large-scale systems. And interesting behavior you see when you combine very simple elements, simple dynamical system, but a lot of them. And today his talk is going to be on that topic as well. So he's going to share with us his new results on this area. Welcome. And
thank you very much, Professor Mine. Also, thank you for inviting me. I'm very happy to be here. We've actually published a paper, right?
Yeah.
Yeah. And we're trying to work on another one as we speak. What I'm going to do is I'm going to talk about decentralized control of large groups of agents. And in my case, or in our case, we tend to think of that as cars in traffic. But that's not necessarily the case. It's just a hang-up to do this problem. I, of course, come from a slightly more mathematical point of view. But I tell you, I started this problem in about 5-6 years ago. I started looking into this, and I wanted to do something really interesting having to do with graph theory and ordinary differential equations. And I was looking for an easy problem to do. And that's how I started the problem. So I thought, I'll do the linear case because that's easy. Everybody knows how to do that. And of course, I never moved beyond it. And in fact, it's so bad now that I gave up on the mathematics, as you'll see, halfway or 2/3 into the talk. I gave up on the mathematics. It's just too hard. I can't do this problem. I actually had to bring in physical intuition to get ahead, to move ahead with the theory. So I'm going to have to state things that I can't prove, which is suicidal for a mathematician. But in engineering, I guess we can do this. I want to start by explaining this picture, and I'll try to move it so to the beginning. It's thinking about drawing it. This is sort of a big picture. It takes a little while to draw. What this is, and I'll show you the axis. These are 1,000 trajectories in R. So this is R, as you can see. What happens is the leader, this is the position of the leader. Now the leader sees a traffic light, and the leader decides to move ahead with constant speed. Okay? So the light turns green. His speed goes from 0 to 1 instantaneously, let's say, and he moves ahead. There's a camera mounted on the leader, and the camera records the positions relative to the leader of the other cars. Okay? And that's what you see. Of course, this is not a movie. This is just numerical simulation. So the leader looks like it stands still, but that's because the movie picture is taken from the leader. The last car, that's number 1,000, so this is position, this is time. The last car, you'll say, how can that be? It moves away from the leader. No, no, no. What happens is the leader, remember the camera is mounted on the leader, so the leader sees this car disappearing, right? Because the leader is moving, he hasn't gotten the news yet. Okay, there's a certain response time. This is where he figures out, hey, we're moving. That's similar. We think it's similar as to when you're in traffic and you see the guys, you see 10 cars ahead, they're already moving, but you still have to wait. Or in fact, yesterday my plane was delayed, and when you exit a plane and you take your bags and you can see them moving way ahead of you, but it takes a while for you to get there. That's actually a phenomenon that's universal to anything that is in a chain and that has mass associated with it, inertia. So that's what happens here. So this guy is waiting, so this derivative is exactly 1. Here he gets the news. Guys close to him are starting to move, and he starts to move. And then what happens is very interesting. he starts to move. He catches up with the leader, as you can see. In fact, in this simulation, he surpasses the leader. So everybody's dead anyway, but never mind. So it's only numerical. He catches up with the leader. Okay, so he goes faster than the leader, he catches up, and then what happens? He tends to stop again. Same thing happens, except it's slightly attenuated. If I would, this is a lot of cars, so it took a while, and the program wasn't written for this many cars, so it calculates too many things and it draws too many things, so it's hard to iterate this very longer. We usually use 200 cars, and then I can make drawings much more easily for much longer time. But what you'll see, and you'll see examples of this later, it will diminish and it will finally die out. So as a dynamical system, that's my original area, as a dynamical system this is stable. But obviously if you have your car, if you're going to have a chip put in your car and that chip does this, the knowledge that that system is asymptotically stable is not sufficient. You don't want to sit in those cars. Because if you did, you die no later than here. Okay? Right, that's where everybody collides. And so what we're investigating is what is called transients. And so I'll start the official talk. Are there any questions about this picture? By the way, I'll show some more simulations. This kind of situation we can analytically essentially completely understand, and I can, I'm not going to do it today, don't worry, but I can calculate exactly what this orbit is, and the orbit is indeed a curious zigzag pattern. If you're not standing with the leader, what happens? What happens is that indeed the last guy waits, then acquires twice the velocity of the leader, and then tends to wait again, acquires twice the velocity of the leader, and zigzag, stop and go motion. As you probably recall from many traffic situations. So we actually can deal with this analytically, and on the basis of a system of linear ordinary differential equations. Is the picture clear? Because that's sort of the starting point. Feel free to ask, please. Because that's all I'm going to talk about. So if the picture's not clear, I'll make it more clear. No questions? This is the coast of Oregon, by the way. But that's not really that relevant at this point. Okay. Pravir said maybe I should use full screen and then magnify a bit. Right, Pravir? Is this okay? Carlos is a student of mine, and that's the official name of our department because of a large donation we received. And this is based on a paper that we're writing. Now the thing is thinking, because there's so many figures in this. It's based on a paper that we're currently writing, and that part of it actually be considering writing with Prabir and He Hao, who is also here. Right, there he is. Oh. We'll just have to wait. Ah, there it is. So here's the summary of what I'm going to do. The green part, it's supposed to be green, I don't know if you can see that. The green part is the introduction. So what we're interested in is the performance of these models. So we already saw in my little example that the fact that this is stable is not enough. It just doesn't cut it. And we'll see exactly why that is. I'm going to look at, so what I'm going to do is I'm going to model these things by linear things. What they turn out to be is oscillators. You model these things by masses connected to one another with springs, linear oscillators. Yes, go ahead.
What's the definition of stability here?
Of a what?
Stability.
I'll get to that, but stability means that eventually the motion is synchronous. They move in one coherent movement, as cars do when everything goes fine. The entire flock flows with more or less constant distance between each other. Okay? Or when birds fly by, actually my motivation was biologically originally. When birds fly by, they move in unison. And so that's for this case, that's the equilibrium state. Okay? So I'm going to tell you what the model is in the green part, that the first lines are green. I'm going to tell you what nearest neighbor coupling is. We don't necessarily restrict to nearest neighbor coupling in our research, but for this talk I will. I'm going to tell you what the questions are. The questions are obviously, is this thing stable? And stable in the sense of ordinary differential equation. And we will make sure that the systems are stable. But then the second question is, and I'll define that precisely, the second question is, well, what about these transients? Because I didn't want to be part of that system that I started this talk with. And that notion, which I'll define in the rest of the talk, we call flux stable. There's other notions in the literature by Swarup Darba, I think was one of the first to formulate string stability, but we don't use that. And then we'll ask the question, well, what now that we understand this a little bit better, how can we qualitatively say which systems are the best? Because it turns out there's parameters that you can choose. So how do you choose the best possibility if you're actually going to build these systems? The complications. And I have arguments with Prabir about this, but in the literature mostly this problem is studied in the frequency domain. That's interesting and very useful, but it really doesn't tell you what the motion is in the time domain. There's an inverse Fourier transform is lacking. That's really relevant because those inverse integrals are very hard to perform, and it's not clear what the answer is until you do it. It's also the hardest part of the problem. Okay, these transients. The other part of the problem is that in much of the literature, the transients, they are not. You cannot study them by using only eigenvalues. That is well known. It's not new, but it's not always observed in the literature. Another problem is there is no theory available for the boundary conditions. What we're going to do, every car looks at the guy behind him and the guy in front of him. But of course, the last car, there's a last car because the thing is finite. He can't do that. So you have to do something else. That's called a boundary condition. Okay? How you choose the boundary condition may or may not influence the result. It's actually unknown as far as I've been able to investigate. So what we try to do is find a strategy that is independent of those boundary conditions. And that's what I'm going to formulate in the blue part. In that case, and so the blue part is where I just give up the math. I can't do the problem. I just throw my hands in the air and say, okay, here's a conjecture. Believe this. Now I can do something. If you do that, you can sort of more or less completely study the problem, at least the nearest neighbor problem. And I'll show you some results. And some of those results are counterintuitive, that you wouldn't have expected. So the key words, and I'll explain all of these, in fact, because I already had a question, are asymptotic stability, flux stability, non-normality, phase velocity, signal velocity, Lyapunov exponents, for those of you. So I start with introduction. So this is a pictorial representation of the model. Here is my mass. And for today's talk, here is the guy in the middle of the flock. He sees two people, the guy in front of him and the guy in the back. This is a symbol that's used in probably engineering as well, but in physics, to indicate damping. And this, of course, is a spring. So these are linearly damped oscillators. Okay? And I'll explain that. Now, one thing that you probably know from driving in traffic yourself is that you don't necessarily pay equal attention to two people, behind and in front. You may pay more attention to the guy in front, or vice versa. Right? And in fact, if you program these things anyway, you could that's a parameter you can choose. So we're not assuming that everything are equal. We will be assuming that all the machines are built equally. Okay? If I drive a Ford Pinto, then you drive one too. You don't get to drive a BMW if I drive a Pinto. Okay, that's the spirit. So that's the picture. Is the picture clear? Again, I emphasize, in this talk, we'll assume that you only see your nearest neighbors. Then what happens, this guy is red for a reason, this guy takes off. These people only get information from their neighbor, so he tries to follow. This guy as long as this guy directly in front of me isn't moving, doesn't know anything is going on. So he's in a waiting mode. And it's a law of physics that takes time. That's what's called inertia. It takes time for him to be aware that people are moving. Okay? And then the idea is that you want to do this in a way that eventually everybody moves at this constant speed to the next traffic light, and then they stop again. And can you do this by only local interactions and no outside information? That's what's called no outside information, at least in my interpretation, that's what's called decentralized control. And I'll be very strict about that because I'm a mathematician. Here's the story again. The agents, I don't know if I said everything. In general, of course, with more general situations, especially with birds, you have to think of these things as on a graph. So they communicate along what we call a communication graph. I'm not going to address that here. In our case, we have, of course, a linear graph, very simple. Identical agents, of course, again, accepted boundaries. If you have a two-dimensional sort of flock, remember, your boundaries are big, right? So that's an issue if you study actual biological movement. These fish in a school that swim and somebody sees a shark or whatever and they try to, that's very complicated. But I'm not going to address that. So the main application that Prabir and I work on is, we think of this as a single lane problem with dense traffic. How to best move the most of the cars with the least, using the least amount of energy, the least oscillation, the least damage. And by the way, this is, remember we have models with inertia, but this is very widely used in neuroscience and they call it synchronization, how to get things to move coherently. And that's called synchronization, and it's a huge topic. Half of all physics departments work on it in the nation, I'm sure. Half of all physicists, I mean. Oh, what happened? Oh, it's thinking again. Okay, let's see. I just repeat the drawing to remind you. What I need to know when I'm behind you, you drive in front of me, I need to know what our desired distance is. If it's too small, if our desired distance is delta, and my real distance, you're in front. The agent k minus 1, as you see in the picture, is in front of agent k. If that desired distance is too small, I need to decelerate. If it's too big, I want to accelerate. Okay? So this kind of term will feed into my acceleration. Okay? So what I'm gonna build this equation that will say, well, the second derivative of xk of t will contain this term. But it will also contain, since I'm doing both neighbors, this term. Okay? Similarly, oh wait, and I can weight those things because, as I said before, I don't necessarily pay equal attention. So rho x is a parameter. This is the weight of the x. We call this a Laplacian, never mind. You can see these are weights. Typically you would take them between 0 and 1, but that's not really necessary. So I'm going to weight these signals. I'm going to weight them with rho x. The one in front of me is rho x. The one behind me is 1 minus rho x. And then I'm going to multiply the whole thing by a gain factor, which is called g of x. It's not a function. It's a real parameter in this case. Okay? So if you add it all up, you get this. If you go through this whole reasoning, you get this term. This is going to be an input term for my acceleration. Okay, so x, double x, the second derivative of xk is going to contain this term. This already has 1, 2, 3 parameters, I think. Now I'm going to do the same. So you're allowed to see relative distances. You're not allowed to see absolute position. That's not decentralized, according to my definition. Same with velocity. You're allowed to see relative... Did you have a question? Sorry. You're allowed to see relative velocities. Okay? So I'm going to get an identical term, but now with dots above them. And not, delta is 0. I want everybody to have the same speed. The difference in speed, the desired difference in speed is 0. Not delta. Okay? So the force on the car, or the acceleration if you want, via Newton's law, is going to look like this. Oops, sorry. There it is. It's going to look like this, plus an identical term for in the velocities, in the x dots. I don't want to take you through all the computations, but you can do a coordinate transform that gets rid of the delta, and the equations look the same. Okay? So you won't see the delta. It's gone. Via linear coordinate transform. Okay? I can write that up a little bit. Now notice, if you look, and that's sort of surprising at first. People say, how did that happen? If I look at the contribution of my own signal, right, except for the gain, here's this weight factor, here is the complementary weight factor. They add up to 1, as they should. Okay, so in my official equation, you're going to see a 1 in front of this thing. That has weight 1 minus rho, and the person in front of you has weight rho. You'll see that reflected in the next equations, which are written up a little bit more economically. There it is. So my new coordinates, remember I had to get rid of the deltas. I wanted to get rid of the deltas. Look, a simplified version, look like this, where these are the weights of the neighbors. Okay? And such that, oh, you can see it, the row zeros are 1. Okay? And the sum of the rows, sorry, I think I don't have all the conditions. Or, why is this complicated? Oh, I say that twice. Sorry. Yeah, so I forgot a condition. The sum of the rows is 0. That follows from the previous page. And the row zeros, your own reference is 1, has the value 1. I say that twice, I apologize. And then there's an external forcing, because remember the leader doesn't, the definition of a leader is the person who doesn't see anyone else. This guy just moves ahead, sees the light turn green, just moves. Okay? The others then try to follow. That's the external forcing. And so these are the equations with the necessary conditions on the rows. Okay? Leader receives no input. Agent N, and then the only thing that I left open, the other exception is, of course, agent N. N is always the last agent. It doesn't see the guy behind him because there is nobody there, right? So that's the boundary condition. So that's how we set up the equations. Are there any questions? Now, the previous looks almost the same, except now I call this a matrix. This now is a matrix. Those rows you could write as a matrix. You can build a matrix out of that. That matrix in math, we call that a Laplacian for physical reasons. The reason is that the rows of the Laplacian, oh, that's complicated to explain. See, the rows of the Laplacian were actually those Greek rows. How do you say this? I got myself in trouble here. Remember the Greek letter rho that I use? Well, those sum to 0. Okay? But that's also the row sum of the Laplacian. This is really hard to say, because the word sounds the same in English. I could say it in Dutch. Maybe that's easier. And so that makes this into a Laplacian. That's the sort of defining property of the Laplacian. Those are special matrices. In particular, this has a solution, z equals constant. And I'm not going to do any calculations today. And that's what the first remark is here. You can rewrite this in shorter notation, more economic notation. Mathematicians tend to be extremely lazy. This is highly complicated. Why is that so hard? Yes, go ahead.
What's the benefit of depending the second agent on the first agent? Why don't you let the second agent move independently of the first agent?
Well, if
because the first agent is like dragging the second agent.
Yes.
Why don't you just put a boundary that don't just get closer than this much to the first agent and move as well as you want?
That's akin to. Okay, think of this in a traffic situation, okay? There's 10 or 100 cars lined up. Big road, okay? Now we give everybody a signal. We blindfold you and we give everybody a signal. Drive 50 miles an hour exactly. The traffic light is green now. What do you think will happen? Right? It won't work.
If they're exactly the same.
If they're exactly the same, but you see now that's not decentralized because now, so first of all it won't work, but second of all it's not decentralized because now you're giving everybody's controlled by God, so everybody's outside information. The whole purpose of this is by local information making the stuff coherent.
You mean there's a time delay?
And sorry.
So you mean there's a time delay between each edges?
Well, there's no built-in time delay, but the physics already gives you a time delay because of the mass involved.
So the agents are not autonomous.
I'm not sure what you mean, but they need to see what happens. Like when you drive a car, you can't drive a car blindfolded, even if you go in a straight line. You need to always correct because your 50 miles an hour won't be exactly the same as the other guys. Right?
By autonomous, I mean that, for example, if your front car is moving, you can, I don't know, wait for the distance to get to a certain extent and then move at the
Oh, yeah.
Or
So I see what you're saying. So if you still, yeah,
dynamics or something
this is
like
sort of a different problem. I'm assuming that traffic is already very dense. Okay, so you need these pilots. You need to pay attention where you are with respect to your neighbors. If there's nobody else on the road, you don't want to study this. If you always drive alone on the road, you probably don't live in Gainesville, but then you don't want to study this problem, trust me. But yes, so there. So that's a different set of problems. The Google cars, they drove, you just told me, right? They drove a car, a single car across country or across Nevada, I'm not sure. And that's a different set of problems. By the way, this is also linear. In a real, if you want to do this for real, when things get really close, you probably want to do something non-linear, just really brake, as opposed to losing your car. Yeah. Okay, so this is the same equation in matrix notation. These are my Laplacians multiplied by the gains. And now we still have 2 rows, 2 gains, kind of 4 parameters, but then also the parameters that you need to vary the boundary conditions. So it's still a huge problem. Remember, this is only nearest neighbor. So this is only the simplest version. And as I said, the boundary conditions, the influence of boundary conditions isn't really known. So it's kind of hard to study. I shouldn't have said that because the remark it says here is, well, this is a 2-dimensional, or sorry, 2n plus 2-dimensional linear non-autonomous system. This is the kind of system, right? d dt of z equals m times z plus g of t. This is the kind of system in our university is called Math 256. The first differential, second year differential, the first course differential equations. So what's the problem? That's what I thought when I started this. And so we'll look at it. So this ends the introduction. It's a good point to ask more questions if you have any. So the first approach, here's what you do. I don't know why this is so complicated to move.
Well, I have so much difficulty. Instead of, you don't want the text icon or the hand icon.
I want this.
Listen, right-click on the toolbar.
View file in read mode. So you want me to press this? You can try it if you want. I don't mind having help up here. It's a big audience. Are you filming this? You want to take over? That's okay.
The next one, where's the? You see right now you select. See this? We're giving you all a lesson in Acrobat. We don't want that. We want a hand. Where's the hand icon?
Oh, I'm not an expert. Maybe you need read mode.
The tools.
If you right-click on the toolbar up there.
Where?
Yeah,
Oh.
right around there.
You sure? Well, that was like.
Oops.
It was still not. You see that cursor showing your hand? Usually you see a hand.
Do it.
Sorry about that.
I thought I found it. So.
Maybe you could do, yeah, this is developing into a whole new talk now.
audience participation. Oh, there you go.
Oh, he's got it.
Oh, yeah, there you go.
Wow. Thank you. You ought to write a paper with that guy. Okay, so let's see if it works now. Oh. Okay, so what is it that Math 256, whatever it's called in Florida, what is it that they teach you? Here's what you do. You find the eigenvalues, I'm going to call them nu, and the eigenvectors v, that's a very similar symbol, but it doesn't matter. Then you find a particular solutions, and to that particular solutions, you add up all these combinations, you add up a combination of these things, so as to fit your initial conditions, and the problem is solved. Correct? That's what you do. So what's the problem with that? Right? This is Math 101, ODE 101. I hope I have a good one for the problem because this is really convincing. Uh-oh.
Page down.
Oh, page down. Oh, there it is, the problem. Oh, man. Ah! That's based on eigenvalues and eigenvectors. So there's a famous applied mathematician who wrote in the 90s, but this was known to John von Neumann, that if this matrix M is not symmetric, in fact, if its eigenvectors are not normal to one another, then the spectrum, the eigenvalues of A, do not determine the behavior of the actual solutions. They only determine the behavior of the actual solutions if t goes to infinity. Now remember, we said we already know the system is stable. We want to know what happens in the meantime before it settles down. Okay, so that method that I outlined won't work. You'll get the wrong answers. Okay, and I'll show that. I'm stating this a little bit more strongly than maybe I should, but it's essentially, there's the truth in that. In this case, let's look at the remember, I have these systems that are essentially arbitrarily large. N is finite, but it's not really bounded by 3 or 5 or 10 or 20 or 100 or 1,000 even. So let's see how this works. If you remember your ODE theory, this is what we teach in our courses, right? Here's your system. Forget the forcing for the moment. Let's just keep it simple. So the system looks like that. Now the n is just to indicate the size of the thing, because I need to keep track of that. It's playing an important role. Now let's suppose that h is the transformation that brings m onto diagonal form. Okay? Then the solution will look like this, where now J is a diagonal matrix. Okay? Now you wonder, okay, so this looks good. This is what we do in class. So what happens? Let's try to estimate how big that solution is. Well, now you have to estimate the size of that. That turns out to be you could do that in terms of the matrix norm or operator norm, if you remember that. That's the size of this thing times that thing times, of course, I'm assuming that the eigenvalues, that the largest eigenvalue still has a negative real part, okay? So this thing is easy to estimate, the size of this thing. But these guys, I don't know. Now it turns out if the eigenvectors are not normal, this thing can become big. Okay? I can't get rid of it because it may grow in n. It's not a constant because remember, my n is not bounded. And it does indeed happen that even though that shrinks, this grows exponentially. So there's a clash, and that's what we mean by non-normality. That's what Trefethen was referring to. Okay? So even though, which is not quite the case, but essentially yes, even though the eigenvalues are always less than some negative number, the real part of the eigenvalue is always less than some negative number, that expression, the max of the norm of z, which is the movement of the last car, may still grow exponentially fast in n. If that happens, you can't have a large flock. They will all die. Okay? On the other hand, if this thing has an orthogonal basis of eigenvectors, then, by the way, this is called the condition number of the matrix Hn, and it's very well known in computational mathematics, a very well known quantity. If, of course, M has an orthonormal basis, then these eigenvectors are all normal to one another. So if you take the norm, you get norm 1. I'm not going to prove that. I don't want to prove. But just take it from me. That's what I said before, right? So that's what leads to, even though the system is stable, it may still be flock unstable if that thing grows exponentially. So that's what our definition of flock stability is based upon. First of all, I'm going to answer your question about asymptotic stability. Asymptotic stability, we call a system asymptotic stability if all eigenvalues have real part negative. Okay, then for long times, as t goes to infinity, the thing will stabilize. Okay, we call it flock stable if this other term, which I can't point at because it's too high, that condition number, oh there it is, if that condition number grows less than exponentially, then we call it flock stable. If it's exponentially large in n, we call it flock unstable. So you take the log of that number. 1 over n times the log. And if that's positive, you call it a flock unstable. Unfortunately, we can't really calculate that thing. So that's what the problem is. Oh, yes, sorry, page down. You just says already. Here's a dramatic example. We proved this in previous papers. We changed one parameter very little. Now, this is the same picture as I started out the talk with, but now the leader, this is taken from the point of view of a bystander. Somebody stands here, this is the road, and the leader starts, I hope you can see it, yes, it's slanted, I think you can see that, right? So the leader will start, and what people do, they look equally forward and backward, okay? And what you can see very clearly in this more concise simulation is that this guy stands still and then starts overtaking the leader. Then when the crowd or the flock is at its thinnest or least, what do you say that, least spread out, he stops again, okay, and waits again. And so that stop and go motion, that motion, because of the eigenmodes that gradually die out one by one, will then get rounded off and finally will die out. Okay? Here's what happened. So what I did to get this simulation is we chose our parameters in several ways, but the one thing we did is you pay, those weights are 1/2, all of those weights. So you pay equal attention, equal amount of attention, if you want, to the person in front and to the person in back. And there's a boundary condition which I don't want to talk about. Now what I did, and I always forget which way it goes, what I did here and here, I paid 55% of attention to the guy behind me. 0.55 instead of 0.5. Here I pay 55%, 0.55 instead of 0.5 to the guy in front of me. And see how dramatic. This will take a cosmic number of years to converge. I mean, we're talking in, you know, I can't even finish the simulation. I don't have patience. I know what's going to happen, but so I never finish it. It takes an enormous amount of time. Everybody will spread out and go. That's incredible. I do almost the same thing. I pay almost equal amounts. And yet, my perturbations grow immediately, jump exponentially in n. These things grow exponentially in n. This is actually proved. We can prove this. This is no conjecturing in this. It's not easy to prove that. I'll get back to it. This is the what do you call that? The Fourier spectrum. Maybe I shouldn't much pay attention. And that actually has to do with Trefenden's comments. But I don't want to maybe... I want to, so this is the typical, yeah, I want to make that comment. So this is a transient, right? Well, that's a transient, it's really small. This guy, by the way, grows linearly in n, which is extremely interesting, which means if I take a larger crowd, this is 100 cars. If I take 200 cars and I stand twice the distance away from it, I see exactly the same thing, which is kind of what you would expect. right? And for a natural phenomenon. So it's scale invariant. Right? If you make it twice as big and you take twice the distance, you see exactly the same thing. No difference. This, if I make it twice as big, I don't know the exponent, but this grows exponentially. So this grows way more. Same for the other guy. After a long, long time. Okay. Those are called transients, okay? Because the thing is stable. Every system is stable, as you can see. Let's look at the eigenvalues. And here the surprising thing happens. Oh, I keep forgetting. This is the first system, the thing that oscillates wildly. This is the central system, and that's the only one I want you to look at, that I'm going to talk about it anyway. Look at the eigenvalues. This is really strange, because these eigenvalues sit close to the real axis. Those don't. But that's where I get the exponential behavior, and that's only linear. The cause of that is non-normality. Okay? For a mathematician, that's really odd. I don't know if you mentioned it or one of your colleagues first, because non-normality, to treat that as though it's a special case is really weird, because you take any matrix, of course the eigenvectors are not normal. It's not really a special case, it's what you expect. But in applications, we're so used to dealing with certain symmetric situations, we got used to matrices being symmetric, and we forgot kind of that the normal phase, the normal station of life is not being symmetric. And so then you really get these phenomena. Okay, I just want to impress that. So you can see the problem begins to complicate. Here is the third spectrum. Let's skip ahead. Oh, I need to do this. Now let's talk about the boundary conditions. That's the hardest part, because not much is known. And so we have several examples. We took several cases. Here is my equations for the z's. Remember, the deltas are gone. And so this would be my last equation. N is always my last person. Okay? If I replace, so this would have been Zn plus 1. If I replace that by Z0, that's like putting the thing in a circle. That's what's called periodic boundary conditions. It's going to be a little bit confusing because I'm going to look at two systems of this type. One unforced and one with a leader. Okay? And they have completely different behaviors. Other boundary conditions, we need a parameter or two parameters, at least. Remember, this is still a simple case. Do I need to? Yes. So what I can do instead, if I don't want to look at the first one, which is not really fair, but I'll tell you why I do that later. Because, of course, in a highway situation, that's crazy. We're not driving around in a circle. Well, maybe some people do, but it's not. Actually, in Japan, they did an experiment with that, but it's not really the common. So the normal situation is that you only see yourself and the guy in front of you. Okay? Now you have a choice, because, for example, what you can do is, well, the other people give weights of the person in front of me 1/2. So in that case, that's what I do, and I just forget that I had someone behind me. That's what I do. Or you could say, now wait a second. If from a physical point of view, you can interpret this beta as a mass. So in that case, you say, oh, beta's really got to be 1. The advantage of doing beta is 1/2 in the symmetric case is that your matrices, certain matrices become symmetric, and the mathematical analysis is easier. From a physical point of view, it's probably not as realistic. And then the question comes up, well, does it make a difference? And the answer is we don't really know. And I'll comment on that. We didn't really know, or at least I couldn't figure anything out in the literature. So those give me three sets of boundary conditions: circular, symmetric, and what we call regular. Of course, there's a whole 2-parameter set at least. As I said, the case most studied, also by us, is the symmetric case with both rows equal to 1/2. In that case, we sort of understand completely. The most realistic boundary conditions is, as I said, at least from my point of view, is, I said, the regular boundary condition. It's not clear, it makes a difference. That's one of the things we want to find out. This I already said. A system is called asymptotically stable. I just repeat it. If all its eigenvalues have negative real part, you can easily see that if that is the case, and I let the leader execute a harmonic motion, right? The real part of that is just sine omega t, sorry, cosine omega t. Then that same motion will be copied by the others. That's easy to show, except with multiplied by a amplitude. Mind you, that amplitude can be complex, so there can be a phase delay. There will be a phase delay. And then one of the questions you can ask is, how big is that frequency response? As I said, what I'm more interested in is an actual time response. What if this guy leaves? What if the leader leaves at 1? So the leader sits still until time 0 and then moves away at velocity, at constant velocity. The response to that is this for the case, and I want to estimate that. So that tells me, that leads me to the definition of flux stable. I look at that k, that zk of t. In fact, for the system I'm looking at, essentially it's the last guy who moves the most, and I take the max, and I want to know what's the worst case, and how does it depend on my parameters. Okay, if that goes up exponentially in n, I call the system flux unstable, even though, I switched my definitions around. Sorry, this line should go here and this line should go there. The frequency response, impulse, this is the impulse response, this is the frequency response. I apologize for that. I hadn't seen that. For this talk, I'm not going to really look at the at the frequency response. So we're going to look at that expression on top of the screen, okay? And if that grows exponentially, we say it's flux unstable. That's the message. Okay, here's more simulations, just to show you what happens if you change boundary conditions. Same kind of picture as I started out the talk. The camera is mounted on the leader. Of course, this is a numerical simulation. And this is with boundary conditions. This is with regular boundary conditions. Here what I did, this is essentially periodic boundary conditions. Now I want you to pay attention to two details. There's a little bit of trickery going on here, but I don't want to get into it. I want you to pay attention to two details. If I look at this, so we start with 100 cars, we started right here, same as the other picture, and then we move to, I don't know, it looks like 148 or 150. It's almost the same here. It looks like 146 or so here. And then, but then the story changes. This dies out quickly. That takes its time. The only thing I changed is the boundary condition. Okay? This tells you that if I change boundary conditions, there's no hope. It looks like, I'll make that a little weaker. It looks like there's no hope for me to predict the attenuation as a function independent of the boundary condition, because it apparently depends on the boundary condition. From a mathematical point of view, that is reasonable, because if this, I'll explain that later. From the eigenvalue problem, from the eigenvalues, there's something interesting going on. There's a problem with MATLAB and eigenvalues. I don't want to emphasize that too much. But you see, the red system is a reference system that I don't want to talk about. The blue system are the eigenvalues, the blue dots are the eigenvalues of that system. And this is the magnification. And here you get the other system. Okay? You see they have moved a little bit to the left. The blue things. They're not close to 0 as opposed to the reference system. And that seems indicative of something. We're actually hoping to take up that study with He Hao, right? I think, yes. And Prabir, of course. Oops. This is the other system, and you see that didn't happen. Okay, so that's one of the things we're trying to study. So the Lyapunov exponent are going to be different. Let's see. So how do we solve this? Well, by keeping, oh, here we go. what we're going to do is we're going to define a normalized systems. I'm going to find myself a system that's simple to study, and then I'm going to dream. I'm going to conjecture. I'm going to conjecture that what I pretend to solve is independent of what system I chose. So I'm going to find myself a particularly simple system, and then I'm going to say, okay, what I want to study is the same in this particularly simple system as it is in the more complicated systems. And then I find the answer for the simple system, and I say, I'm done. So this is where I lose touch with mathematics. And I'll explain that a little bit more precisely. The normalized system is the system with periodic boundary conditions and no leader. So you can give people initial velocity, but you can't, there's no external forcing. Okay? I'm going to use that system to predict features. I need to move the screen. To predict the features that apparently are independent of the boundary conditions. And so here are the conjectures. One, essentially my conjectures is that the velocity of traveling waves, obviously we thought about this a little bit. And so if you think about this, the conclusion you come to that the following should be true. The velocity of traveling waves does not depend on the boundary condition. That's reasonable, because if you have a wavefront traveling through the system, rippling through the system, that is far away from the boundary. So until it hits the other boundary, its speed shouldn't, the signal velocity shouldn't depend on the boundary condition. I cannot, however, prove that. And I've asked around, so I haven't met anyone who can. Doesn't mean that nobody can, I just haven't seen it. I also need to know that the eigenvalues of the system, in some sense of the word, become close. So if I take a million-dimensional system, I twiddle with a boundary condition, I sort of get the same eigenvalues as when I twiddle in a different way with the boundary condition. That's not necessarily clear. Okay, and so those are the kinds of things. If you do that, then you can choose your boundary conditions so that you get the simplest system of all these systems, and that's the one you study. And there's one system in which we can study this, the velocity of the traveling waves. Okay, and that's, we'll look at that. I guess I'm running late, but anyway. And that the normalized system has a nice sort of spectrum. This is it. You get beautiful curves out of this. And here's an example of spectrum. This spectrum I can calculate, I can understand analytically. Okay, to a large extent. Oh, this is beautiful, but I don't really have time to show it. And so this is a 3D rendering. The reason is these, if somebody's artistically inclined, these are very beautiful curves. You can render these in 3D with MATLAB, but I can't get MATLAB to work for reasons we don't know. But otherwise, I'd show you. So this is a 3D, and you see these. So the third dimension, this is obviously the complex plane. The third dimension is the index of the eigenvalue, which eigenvalue it is, and it gives you beautifully closed curves in the complex plane times r. Anyway, that's just. So what are the implications? First of all, the implication is this. If I take that row x, remember I have two rows, the weights on the x component of the Laplacian. If I take that row x, if that is not equal, this is an example, if that is not equal to 1/2, here you can see, this program is intended to study the next nearest neighbor, but we just keep the outer side 0. So these are the values of rho in, the guy in front of you, yourself, and the guy behind you. You can see it's not 1/2. What happens in the model system is that the spectrum acquires a positive real part. Now that conjecture kicks in, that second conjecture that says that if I make my system sufficiently large, then also the system with non-trivial boundary conditions will look like this. and therefore must have a positive part. And therefore is it asymptotically unstable, and the thing will explode. Okay? We've obviously tested this a gazillion times. It always works, but I still can't prove it. So I use it as a conjecture. Okay? The fact that this is so, I can obviously prove. So what happens if you wanna use this algorithm for a flock and make it make sense? You are forced to choose that first Rx, I call them rho x, minus a half, 1 and a half, minus a half. Otherwise, the system will be very unstable. So I will do that unless I mention otherwise. Just a technical, is there anyone in charge? Because if I run over too much, who's in charge? Because, do you want me to not run over time? I mean, okay. Or I can temporarily close, and then if people want to hear more. The second consequence is, and then I'll make a pause, because in case other people want to leave as well. The second consequence is that is this traveling wave phenomenon. We can actually, and I won't go through it, but we can actually, for that simple model, is in technical terms, it's diagonalized by the discrete Fourier transform. And that means you can find phase velocities. I can actually find those velocities with which waves propagate. And it has to do with the imaginary part of the first eigenvalue. If you then sit down and study this a bit, you realize you can actually, for this normalized system, as I call it, you can actually calculate this thing. You can express it in terms of the parameters. And there is what that happened. So that tells me what the velocity is. Now remember what happens. Why is this important? Well, this is important for the following reason. I have a bunch of cars here, and the first guy leaves. Then the distance between him and the first car gets bigger. That's like and then the second car leaves. The distance between him and the third car grows. So this is like a traveling wave through the system. It's not like, it is a wave traveling through the system. That's why the velocity, the wave, the speed of sound, if you want, is important. That's the speed of sound. If you think about it, that tells me when the last car leaves. If I know how fast this thing propagates, I know when the last guy takes off. The moment the last guy takes off, the first guy has traveled X amount. He has been traveling with constant velocity all that time. So if I know the velocity of the signal, I know the response time, and that means I know how far the first guy has traveled. This is the answer. This is that distance. So this is this first amplitude. This is the size of the first amplitude. This is the size of the first amplitude in the normalized system. The conjectures imply that this works independent of boundary conditions. Okay. You want this amplitude to be small. Okay, so it's kind of, there's still a lot of parameters to choose. There are other implications, but since I'm late anyway, I will skip that a little bit. Remember, I can't predict the Lyapunov exponent, the way it attenuates. Let's see how good this theory is. I think that's the next part, or the...
You can go until 3:30.
Oh, till 3:30. Yeah, but I don't think people don't want to... I'll show you some pictures and then I'll quit. By the way, how good is this theory? First of all, in the case that we can do analytically, which I showed you before, where all the rows are equal to 1/2, we can exactly calculate what the orbit is. That's the blue thing. We can also numerically calculate what the orbit of the last car is, and you can see at this resolution they're absolutely identical. And indeed, if you look at this expression, and I put it here on purpose, you get 2, if the rows are 1/2, if rho is 1/2, you get 2 over, no, the root of the square root, sorry, the square root over 2 over g. G is negative, so minus g is positive. The square root of 2 divided by minus g, right, if rho is 1/2. So this verifies that that answer is correct for a system with non-trivial boundary conditions. I cannot prove this. I can only prove this if I assume the conjecture. The conjectures. So let's see how good this theory is, because maybe it's all a lie. This is the Lyapunov exponent. What happened? Oops. How did that happen? I thought okay, so it doesn't want to print the left part of the picture. I don't want to dwell on this. The Lyapunov exponent. So what we did here is we ran with different boundary conditions and we measured the Lyapunov exponent. We already know that we're going to get bad answers. We saw that. So this is expected. The theory doesn't talk about this. This is not. This. Oh, it is what it is. But let's see. So indeed, they're not close. I don't know why this happened. I apologize for not having the whole picture. This is the amplitude, and you can see with for different rows and different values of parameters. There's 4 colors, and there are 4 different boundary conditions. They practically coincide at this revolution. So this theory works, and in fact, I don't restrict rho to between 1 and 0. It works way outside. This is the amplitude, by the way, vertically. So the amplitude is a lot smaller here. The rho 1/2 is here. Why didn't I go to rho positive or rho bigger than 1/2? It turns out the system is asymptotically unstable. By the way, rho x is a half. That was forced upon us. So this is a study of only the rho v. Okay. That's in fact something we're working on now. And that basically ends the talk. I have more pictures like this. And so I'll quickly show them, but they basically convey the same message. This is still work in progress. We don't quite know. There's some problem with the actual measuring this numerically. And so not all pictures, these look particularly good, but they don't all look good. These look not as good. This, by the way, is the period, the length of the oscillation. And we can't measure the light blue one very well, and that probably explains why it's a little further apart from the others. We think it's going to look better when we get that repaired. So this theory works pretty well. There's unsolved problems, and again, I don't want to measure, I don't want to get into this. Some of that we're working. Of course, the main unsolved problem is, are these conjectures even true? I don't know if there's anything else really interesting that I ought to mention. Yeah. Oh. Of course, the Lyapunov exponents we don't know, as I mentioned. But I think I'm going to leave it at that. So we're working on some of these problems with He, How, and Prabir. Since I'm late. Oh, these are references if someone wants them. But I'm sure you're not going to want to see them right now. And so that's more or less what I have to say about this. Are there any questions?
How did you choose the spring parameter and the damping parameter?
In the last set of pictures, so we vary them as much as we can. So we try to cover a lot of range. So in other words, the idea is that this theory now applies to all parameter values, essentially. We're trying to write down a general theory that applies to all choices.
Because if the spring is infinity, then or it just becomes a hard thing. You will still move at the same place at the same time. There's no kind of.
If the spring becomes infinitely long, you mean?
The spring more stiff. Yeah, the most stiff, it becomes most stiff, then there's no oscillation exist anymore.
Right. So the damping is in the velocity. So that's the GV. Those G's are negative. So let's go back to that expression, if I can find it quickly, because sorry, but that's the expression. So if GV becomes huge, then the amplitude goes to 0. Of course, you can't have, from you're all engineers, I guess, you can't have an infinite gain. That's not possible. So the question is, what are realistic choices and how can you optimize? Does that answer your question? Yes?
Is this proven that this mass spring model is the optimal modeling for this to have the tight
As I said, I think earlier, it's not optimal. Linear model is because it's the only thing we can really study well enough to make this kind of detailed sort of predictions. Nonlinear models are much harder. And then again, if you have a nonlinear model and it's in an equilibrium situation, you want to linearize to find the stability of it. And that's when you would get this kind of model. So this is the starting point, but once you decide what this model should be, then of course you'll make a nonlinear model, because if you get really close in an emergency, you probably want to brake, right? So you want to add collision avoidance to this.
And you mentioned that this
at least
stability is related to the value of h, if it is negative.
H, you mean?
I mean the oscillation.
There was a matrix H.
Yes, yes. I mean, so what's the intuition for the condition of having convergence or not?
Okay, there were two types of stability. Asymptotic stability and Floch stability, which...
Flux.
Okay, so if eigenvectors are not normal, then you have a problem. Okay, and then you easily can get Floch instability. When exactly this happens, that's exactly what we're trying to find out with the study. Okay, and the main, let me think. So in these cases, in the last formula, when rho x, okay, let me go back to one picture. Okay, so these are measurements, sorry, I apologize, of the for certain parameter values. Here rho is varying, and from picture to picture I vary other parameters. Vertically, so horizontally is rho, vertically is the amplitude, right? That's the amplitude divided by n, I should say. Okay, so you can see these are all non-exponential cases. These all vary linearly, except when rho v. So this is only rho v. Rho x must be a half for the thing to be stable. When rho v is bigger than a half, the thing is actually asymptotically unstable, it turns out, even though we can't prove that. So I didn't include that in this. When rho v is less than a half, the thing is asymptotically stable and Floch stable. But within being Floch stable, you also want the smallest, the best. So it gets better the less rho is. And surprisingly, when rho is negative, it gets even better. And that's counterintuitive. But you have observed similar, actually Prabir and Hihao have observed similar things. But I guess you guys didn't have the theory. And so we're trying to write part of this together.
I've seen some works at the relaxation of the mass spring systems for a graph of mass springs, but this is like a 1D system of mass spring. So what's
in higher dimension?
No, for example, a 2D mass spring system, the graph of the...
More complicated. And it depends on the application. The equations are much more complicated. Of course, you can formulate this theory, so we will work for this.
But you're usually working on discrete time. You're doing it...
Oh, yeah, I haven't seen that. Okay, we could talk later. We think this theory is now developed enough so that we can attack those higher dimensional problems and actually get answers for amplitudes, which are not in the literature as far as I know. There are other problems that come up, different problems. Usually in 2D, if you have a flock like birds, okay, so here's the bird. Okay, if they fly that way, they fly that way. They typically fly in a V, right? Geese or whatever. But now they change courses. They're going to go east, that way. Okay, they're not going to fly like that. The whole flock is going to turn. Okay, if you incorporate that in your equation, you are forced to write down nonlinear equations. So that is a completely different ballgame. Okay, if I'm allowed to do this, then this theory would apply. It would just be a more complicated version of this theory. And that theory, I think, with him or with them or otherwise, will be developed in the near future. This is so far only one-dimensional, but it can be generalized. It's now good enough to be generalized. But if you do this, that's much more complicated. So that's an extra problem.